Hi, my name is Yosanan Mimak, so you can call me Yot, and I am a professor at Department of Mathematics, Chulalongkorn University. So I'm gonna teach you after the midterm. The topic will cover about the total differential, about the extrema, and uh, extrema of the several variable function, and we're gonna also talk about the Lacan multiplier, and we're gonna discuss about the differential equation and different equation. So that's gonna be like the 7 topics in the after the midterm, okay, for the final exam for calculus 2 BBA. So I will give you the handout, okay? So you see the handout on the blackboard, and I also have the handout on the, I, I will have the handout link on the bottom of the clip also, okay? So you can see the link for the handout at the, like the caption for the clip. So the first week that we gonna study is gonna be about the total differentials. The total differential is gonna be about the thing that you may have seen in calculus 1 or not. Okay, so the first topic that we gonna do is gonna be about the linear approximation. So we can use the tangent line at AFA as an approximation to the curve y equal to fx when x is near a. So this one is the first thing that I like to talk to you in this lecture. So if you see this one, okay, so you see that you have your curve y equal to fx, okay, and you have AFA, okay, and you have the tangent line. So this guy is the tangent line at AFA, okay. And if you wish to find the approximation, okay, so if you wish to find the approximation, so if you have like a y at this point, so this one is going to be a plus delta x and f a plus delta x. So you wish to find the approximation at this point. So in order to do that, you're gonna just use the value at the tangent line. Okay, so you're gonna use the value at tangent line. So here it's gonna be L at a plus delta x instead. And this one turned out to be easier to evaluate. Okay, so this one is gonna be the value at the tangent line. So it's gonna be LA plus delta X. So this one is the clarification for this first sentence. So if you see this one, okay, so if you see this one, you have y equal to square root x plus 3. Okay, so if you have y equal to square root x plus 3 and you have a equal to 1, okay, so I go to this example first. So you see that you're gonna have, okay, so you're gonna have the tangent line. So this one is your fx, okay, and we wish to find the tangent line. Okay, so this one is the tangent line at a equal to 1. Okay, so if you wish to find the tangent line at a equal to 1, the thing that you did in calculus 1 is going to be you need derivative f prime 1. Okay, so you have f prime 1, you have fx equal to slope. Okay, so that will give you the slope. And in order to find the tangent line, you need point. Okay, so point it's gonna be a equal to 1. So it's gonna be a equal to 1, and you have f1 equal to square root 1 plus 3 equal to root 4. So it's gonna be equal to 2. Okay, so you have the point is gonna be 1, 2. Okay, and f prime 1 will be, you have fx equal to square root x plus 3. Okay, and you have f prime x equal to 1 over 2 square root x plus 3. Okay, so it's gonna be like this, and so you're gonna plug in, so you have f prime 1 equal to 1 over 2 root 1 plus 3. So this guy will be 1/4. Okay, so you have the slope equal to 1/4. Okay, so you have the slope equal to 1/4, and you have the point is equal to 1, 2. So you're going to use point slope form in order to find the equation of the line. So this one is going to be point slope form, and it's gonna be y minus 2 equal to 1/4 x minus 1. So you have the slope equal to 1/4. Okay, so in this case you're gonna get y equal to 2 plus 1/4 x minus 1, and this tangent line will be your linearization, or it's going to be Lx. Okay, so this one will be your Lx. Okay, so this one will be your Lx, and you like to find the approximation of square root 3.98. So you see that square root 3.98, I'm going to use this space here. Square root 3.98 turn out to be, you have x equal to 0.08, right? So this one is going to be 0.98 plus 3. And this guy turned out to be f of 0.98. Okay, so you like to find f of 0.98. If you zoom this guy, okay, so you have 0 and 1 like this. So you have 0.98 turn out to be this kind of close to 1. Okay, so 0.98, okay, is here. Okay, and you like to find the approximation for this one. So you see that it's very, very close to the tangent line. So you see the tangent line and you see the curve. So you see this guy is the tangent line and this guy is the curve. And you see that at 0.98, they are very close. So this way, this is what we gonna use to give us the approximation that we are looking for. Okay, so in this case, you're gonna have square root 3.98 equal to square root of 0.98 plus 3 is gonna be equal to f of 0.98, and this guy is about, okay, so this guy is about L 0.98, and L 0.98 turned out to be 2 plus 1/4, 0.98 minus 1. Okay, so it's gonna be just 0.98 minus 1. And you see that this number is quite simple. So it's gonna be 2 plus, and you have negative 0.02 over 4. Okay, so it's gonna turn out to be 2 minus 0.005, I believe. Okay, and it's gonna be equal to 1.995. Okay, So this one will be the approximation for the square root of 3.98. So this is the approximation that we mentioned with the yellow color. So this one is going to be the value of the function. Okay, so this one is the function. And for this guy is called the linearization. Or this one is going to be just equivalent to tangent line. Okay, so this one is going to be just the tangent line, and this guy is going to be just the function. So this one will allow us to just find the approximation by using the tangent line. Okay, so let me go back to the lecture a little bit. So the lecture here saying about the reason why this guy is kind of working, because you see that an equation of the tangent line turned out to be in the point slope form. So this one is going to be just point slope form. Okay, so this one is going to be just the point slope form, and the slope that we have here is going to be just f prime a. Okay, so the tangent line turned out to be this one, and you see that if you have x minus a kind of small, so if you have this guy which is x minus a turn out to be kind of small in this case, you're going to be able to approximate. Okay, so you're going to be able to approximate your function fx by f a plus a prime ax minus a, and this guy is your lx. So this guy is your lx, like this. Okay, so this one is going to be your lx. So this one equal to lx. And lx is nothing else besides it's going to be just the tangent line at x equal to a. And this guy, we have a fancy name called linearization. However, you don't need to know about the name. It's going to be just the tangent line approximation. Okay, so this one is illustrate that. So you see that you like to find this value. Okay, however, the value on the tangent line turned out to be a good approximation. How good it would be? So if you go back to this example, okay, so you see that we be able to use the tangent line approximation to obtain square root 3.98 to be 1.995 like this one. And if you use your calculator, okay, if square root 3.98 is going to be from Lx is going to be 1.995. However, the actual value turned out to be just 1.9949. And if you just like to have 3-digit decimal, this one is correct. Okay, so it's kind of close to the exact value. And the reason why this guy is close, because you see that the point here 0.98 kind of close to 1. Okay, so you see that the point for 0.98 here kind of very close to 1, so you're gonna get a good approximation. Let's try one more. What if you like to find the approximation for square root 4.05? So I'm gonna use this space. So for 4.05, okay, so square root 4.05, okay, so this guy will be square root 1.05 plus 3, and after you have 1.05 here, you're gonna be able to see that this guy is f 1.05 okay, you're going to use linear approximation. So it's going to be 1.05, and this guy will be 2 plus 1 quarter, and you're going to have 1.05 minus 1, okay? So this guy will be 2 plus 1 quarter, 0.05, okay? So it's going to be 2, okay, plus, and you have 4 this guy is going to be 0 0.12, not 0 point, so it's going to be 0 0.0125, okay, so this guy will be 2.0125, okay, so square root 4.05 turned out to be get you the approximation 2.0125, okay, so this one is the yellow guy again, so this one is the linear approximation, okay, and you see that you'll be able to obtain the approximation equal to 2.0125, and you see the actual value. So you know that this guy, okay, so you see that the approximation that you get is 2.0125, and the actual value turned out to be 2.012461. So you see this one kind of like a correct up to 4 digits. Okay, so this one also give you good approximation. Okay, we also have the previous one, which is square root 3.98. Okay, so this guy, you get also a good approximation. Okay, however, you see that if you move further, so if you have x kind of further away from the point that the tangent lie, okay, so you have the tangent line here, and if you have the value of x kind of further away from the value of the tangent line, which is 1 here, so you see that you're gonna get like when x equal to 2 and x equal to 3, so you see that they are kind of further away, okay, so they are not quite a good approximation anymore, so this one is going to be bad and bad approximation. And for this next one, 4.1, this one is so-so, I would say. Okay, so this one is going to be so-so. So I would say it's not good, not bad. Okay, so in this case, this one is going to be, we use the tangent, we be able to use the value at the tangent line in order to give you like the approximation of the given function. Okay, so this one will be just like that. And that leads us to the definition of differential. The concept of differential turned out to be important because you see that you have the graph of the function y equal to fx down here, and you have the tangent line. And you'll be able to use the value of the tangent line to give you the approximate of the value of the function before. However, you see that normally we need delta x to be kind of small. Okay, so we need this guy to be small. So you see in this picture that, hey, it's not quite good approximation. Yes, because the picture kind of large scale. Okay, so in this case, this one I'm gonna say is kind of bad approximation. It's not like in the example that we have seen before. This one is going to be kind of very good, right? So that is gonna be the thing that you may have to concern with. So this one is kind of good approximation, okay? And this one, when you see this one, okay? So when you see this one, let me wait for the program a little bit. So you see that this one is kind of far, okay? So this one is kind of bad. So here you're gonna have dx kind of make sense or good approximation when delta x very small. So you get x plus delta x. And the way to obtain the thing that called differential. The differential turned out to be just like the slope of the tangent line. So you're going to have differential given by dy equal to f prime x dx. Okay, so dy equal to f prime x dx. This one come from basically point slope form. Okay, so this one come from basically the point slope form. And this guy has a name called differential. Okay, so I'm gonna not teach you much on definition. This one is called differential. And one question that can ask you is gonna be, hey, can you, this one we already discussed. Let me go to this one. The previous figure shows that if we let dx equal to delta x, the corresponding change in y is going to turn out to be delta y equal to fx plus delta x minus fx. Okay, and the slope of the line PR is the derivative f prime x. So the direct distance from S to R is gonna turn out to be f prime x dx equal to dy, okay? And dy will represent the amount that the tangent line rise or fall the change in the linearization. So if you recall, okay, so this one is gonna be rise, okay? So delta y is gonna be rise. This one I have to like a recall from your high school. So this one is called rise, and this one normally we call run, okay? And the slope turn out to be rise over run. Okay, so this one is the concept that you have from high school, that when you have the slope of the lines turn out to be rise over run. However, the thing that we need is going to be, we have delta y and dy going to be approximate. Okay, so the approximation, delta y given by dy is going to become better as delta x becomes smaller. Okay, so this one is going to be this guy, and you have smaller delta x. Okay, so we're gonna use the concept of differential, which is gonna be just dy. Okay, so this one is gonna be dy equal to f prime x dx. Okay, in order to obtain the approximation of the value of the function at the design point. Okay, so you're gonna I'm gonna explain the concept more, okay, in the next example. However, let's find like for the differential for each function. So you have a equal to, not a, y equal to square root x e, square root x e to the 2x. So in this case, you're gonna have f prime x or y prime. Okay, so y prime turn out to be square root x, the first. So this one is derivative of the product. So you have to use the product rule. So you're gonna have the first derivative of the second plus the second derivative of the first. So in this case, you're gonna have dy equal to 2 root x e to the 2x plus e to the 2x over 2 root x. And this one is your derivative, right? And you have dx. Okay, so this one is going to be the differential for A. The second one, you have y equal to x squared minus log x. So you would get y prime equal to 2x minus 1 over x. So you have dy equal to 2x minus 1 over x dx. So this one will be just the thing that we used to study, or we used to approximate the change in y. Okay, so when the change in x kind of small, okay, so we need to know this guy. However, this delta y normally kind of difficult to compute, and we kind of use dy instead. So the next one argue about, so you need to use differential to estimate 1 over 3.84. Okay, so if you like to use differential to estimate 1 over 3.84, so you see that we can, okay, so we can compute the actual value by using just the long division. The actual value by, you may just use the long division. So it's gonna be, normally we're gonna have 384 divide 100, right? So this one is gonna be normal thing to do, right? So you just have 384 divided by 100. However, in order to use differential, you're gonna consider function fx equal to 1 over x and find the tangent line at a equal to 4. Okay, so you consider fx equal to 1 over x and you find the tangent line at a equal to 4. So it's going to be just, you have f prime x equal to negative 1 over x squared. So you would get f prime 4 equal to negative 1 over 16. Okay, and you have the point will be 4 and 1/4. So you have the tangent line will be, the tangent line will be y minus 1/4 equal to negative 1/6 x minus 4. Okay, so this one is going to be just your point slope form. Okay, slope equal to 1/16. Okay, and you see that you have y equal to 1/4 minus 1/16 x minus 4, and this one become Lx. Okay, so this one will come Lx. Okay, and you see that 1 over 3.84 is f 3.84. Okay, so this guy can be approximated by L at 3.84, and L at 3.84 will be 1/4 minus 1/16, and you have 3.84 minus 4. Okay, so this guy is going to be 1/4 minus 1/16 negative 0.16. So in this case, you would get 1/4, okay, and 1/4 is 0.25. And this guy, you see that I can do this one without using any calculator at all. okay? And you see this one is gonna be plus 0.01, okay? So this guy will be 0.26. Okay, so this one will be the approximation that I have for 1 over 3.84. And if you compute the actual value, okay, so the actual value for this one become, okay, the actual value, if you use your calculator or you just use the long division, so you would get 0.26041167. Okay, so you see that the approximation that we get is kind of good. Okay, so this one is kind of close to the actual value. Okay, so this one is the way to use the differential in order to obtain the approximation when you like to study the chain of the function. So let me go over the concept again. So the thing that we like to know is going to turn out to be the exact chain. However, the exact chain turned out to be difficult to compute. Okay, so we are looking for some way, another way or some other way in order to obtain the approximation. Okay, so in practice, like in this next example, you have the demand equation for a product given by P equal to 1/2 Q square minus 66 plus 7,000, and the cost function given by C equal to 500 Q minus Q square plus 40,000. Find the profit when 100 units are demanded. So you like to find the profit function. Okay, so you like to find the profit function and you know the demand function. So you know the demand function, so you're gonna get the revenue. Okay, let me do A. So you have the revenue. So you have the revenue function turn out to be P times Q. Okay, so the revenue is P times Q, so it's gonna be 1/2 QQ minus 66Q square plus 7,000 Q. Okay, and you have the cost function given by 500Q minus Q square plus 40,000. So you would get the profit. Okay, so you would get the profit. The profit come from the revenue subtract by the cost function. So you get 1/2 QQ. Okay, so you get 66. So you get 65 Q square. Okay, and 7,000 minus 500. So it's going to be 6,500 Q. Okay, so you have 6,500 Q and you have minus 40,000. Okay, so this one gives you the profit function. So you have 1/2 Q cubed minus 65 Q square minus 6,500 Q minus 40,000 to be your cost function in terms of Q. So this one is the profit. And the question asks you to find the profit when 100 units are demanded. So you need the profit. The profit at Q equal to 100. Okay. The profit equal to, okay. So it's going to be 1/2 100 to the third minus 65 100 square, and you have 6,500 times 100 minus 40,000. Okay, and you see that this one, I think I have the wrong sign. This one is positive, sorry, positive. Okay, so you see that this guy and this guy are the same and the sign are opposite, so they cancel each other. And this one turned out to be, okay, 500,000. Okay, so this one turned out to be 500,000. So this number become for the six, for 4600,000, right? It's 4600,000. So this one will be the actual profit, okay, at Q equal to 100. And the second question asks you to use differential and the result of A to estimate the profit when 98 units are demanded. Okay, so you see that you can plug in Q equal to 98. Okay, so you have Q equal to 98 and the profit turned out to be messy. So it's going to be 98 to the third minus 65, 98 square plus 65, 98. Okay, and minus 40,000. Okay, so kind of difficult to evaluate. Okay, so you can use calculator, I know. However, this one is kind of difficult to evaluate or difficult to get. So we like to estimate. So the question asks you to estimate. Okay, so this is the keyword. So you're gonna use differential. So you're gonna dip the profit. Okay, so you're gonna have profit and you differentiate. So you differentiate the profit with respect to Q. So you have 3/2 Q squared, okay, minus 130 Q plus 65,000. Okay, so this one will be the derivative of this profit. Okay, and you have at Q equal to 100, you get profit prime. Okay, so when you have Q equal to 100, you're gonna be able to just plug in. Okay, so you just plug in Q equal to 100 and you see that this guy will give you negative 65,000 and this one you're gonna Q equal to 100 square. Okay, so you're gonna be able to compute this guy. Okay, so this one turned out to be, okay, so this one turned out to be 1.5. Okay, so it's 1.5 times. Okay, so it's gonna be Q equal to 100. So it's gonna be 3/2 100 and times 100. Okay, let me calculate this one for you. So it's gonna be 50 and it's gonna be what? It's gonna be 15. Okay, so it's gonna be, okay, I need space in order to compute this number. So you have profit prime at 100. Okay, it's gonna turn out to be 3/2 100 square times 100 plus 65. Okay, So this one, okay, turned out to be 1.5. Okay, so it's going to be 1.5. And how many zero do I have? I have 4 zero. So it's going to be, okay, 15,000. And you see that it's gonna be minus 13,000. See, I don't have to use the calculator, plus 65,000. So you have 85. Okay, so you have 85,000. Okay, so we have 85,000. Okay, so you plus 65,000, so you have 85,000. So you have the profit prime at 100 equal to 85,000. So you see that we be able to find the L. Okay, so you see that it's gonna be L at 98. Okay, L at 98. So it's gonna be the point. Okay, so it's gonna be 46. 46000. Okay, L at 98 is 4600, which is the value at 100, right? And 85,000 is the slope. Okay, and you have 98 minus 100. Okay, so let me clear this one a little bit for some of you. So here you have Lx, remember, Lx equal to y, okay, and this guy is your value at 100, so it's gonna be $4,600, and you're gonna add by the slope, which is the slope, and you have x minus 100. Okay, and what is the slope? The slope that we have is 85. Okay, so this one is going to be your slope. Okay, so this one is going to be point slope form that you get. Okay, if you not follow me, okay, it's kind of difficult. Let me change this one for you. If you come from point slope form, you would get something like this first. Okay, so you would get this one. You pretty clear this one is point slope form. Okay, and the slope is 8,500. So you're gonna get Lx equal to y, and this guy turned out to be equal to plus the slope. Okay, and you have L at 80 at 95. Okay, oh sorry, 98 equal to 460 460,000. Okay, you have this guy times this guy, and you see that this one can be calculated. Okay, so this one can be calculated. So for this one, it's gonna be 46000, and you see that it's gonna be minus 170. Okay, so it's gonna turn out to be this number. Okay, so it's gonna be minus 170. So this one will become 44300. Okay, so and this one will be the profit. Okay, so this one is going to be the approximation for the profit at 98. Okay, so this one will give you the approximation for the profit at 98. Okay, however, if you like to evaluate this guy, okay, you can actually, you can have 98 times 98 times 98. I know that you have calculator. It's gonna be, you be able to use Excel. You be able to use calculator. However, we are studying this technique in order to just get the approximation. Okay, so we don't need to go to the actual value. Okay, let's do one more. Okay, let's do one more. You are having the revenue function R equal to uh, 250Q plus 45Q square minus Q to the third. And you like to use differential to find the approximate change in revenue if the number of units increase from Q equal to 40 to Q equal to 41. So the thing that we need is gonna be, we need 41 subtract by 40. So in this case, this one is gonna be 40 plus delta x minus 40. And in this case, your delta x equal to 1. Okay, so and in this case, your delta x equal to 1. And this guy, you see that you can use the linear approximation to find the slope. Okay, and you see that this one is going to be delta x. Okay, or some of you may not think in this way. You can just 40 plus delta x minus 40. Okay, or basically this guy turned out to be delta x anyway. Okay, so this one kind of easy to compute. So you're gonna just find 40 prime. Okay, so let me find R prime for you. R prime turned out to be 250 plus 90Q minus 3Q square. So you get R prime at 40 turn out to be 250 plus 90 times 40 minus 3 times 40 square. Okay, so you have the number that you are having here turn out to be negative 950. Okay, so this one you gonna just calculate. This one is gonna be 60. Okay, so it's gonna be yeah, it's 48. Let's calculate. 250 plus 3600, and you have this guy is 48. Okay, and the total number would be negative 950. Okay, so this one is R prime 40, and you gonna have delta x here is equal to 1. Okay, so you have R, this one is equal to 1. So you have 41 minus 40 is about prime 40, and this guy is negative 950. Okay, is negative 950. So in this case, you're gonna have this one is gonna be the approximation. Okay, however, if you like to find the true chain, so you need, okay, in order to find the true chain, in order to find the true chain, you gonna need 41. Okay, so you're gonna need 41. 41, and this guy is gonna be kind of difficult. So it's gonna be time 41 plus 45, 41 square minus 41 to the third, and you have 40 equal to 250 times 40 plus 45, 40 square minus 40 to the third, and you're gonna just subtract them. Okay, so this one I already calculate this one for you. When you subtract this guy, you're gonna get negative 1026. Okay, so this one will be the true chain. Okay, so you see that this one kind of difficult to compute. Okay, however, if you just like to have the approximate chain, like when you have one piece more in the cell or something like in this situation, you see that the approximate chain turned out to be easier to obtain, and it's gonna be you're gonna be able to use this guy as a prediction or something faster than you find the true chain. Okay, I know that in your mind this day we have computer. Why don't we need something like this? I know this one, but this one is the technique in calculus that you have to study. Okay, we're gonna continue in the next clip about the total differential, which is gonna be dealing with the several variable case when you are having the differential. Okay, it's gonna be approximate again, and it's gonna be like more variable. So this one is going to be just one variable. So if what will happen, or what should we do if we have more than one variable? So we're going to discuss about the several variable function. Okay, so I'm gonna stop here and I'm gonna continue later.